Welcome back to our course on special relativity. In previous lessons we have talked about some issues that physicists saw at the end of the 19th century, when they tried to unify classical mechanics with the electromagnetic theory and light propagation. We already talked a bit about Galilean relativity also. Remember, there is no way to distinguish if we are on a boat or on the shore. The physics is the same on the train and on the station. Something very well presented in the movie Top Secret. So when physicists used Galileo equations to study the propagation of light, they found some weird results. Is there something wrong with Galilean equations? Well, they seem so intuitive and they are very useful when we study classical mechanics. Is there something wrong then with the electromagnetic theory of Maxwell? Well, all our society is based on it. We understand and can make predictions related to electricity, magnetism, and electromagnetic waves. Let's talk now about the brilliant solution that took Einstein 10 years to understand and 3 weeks to write. In the Michelson-Morley experiment, they expected to see the different time of flight from each of the arms of the interferometer. They found no result, and FITZGERALD and LORENTZ suggested that if the other arm had been contracted, this effect would compensate for the time difference. They argued that that was related with the effect of the speed on the structure of matter and made contract matter. A subtype of electromagnetic effect on matter between atoms that at that time were not that well known. But this in fact is a correct mathematical result, but a completely wrong physics result. There are many more examples that point that something was wrong, and many other proposals to solve those problems, but none of them was right. So, what did Einstein do? Albert Einstein assumed two principles and used them to derive the whole theory, solving all the problems and introducing new and surprising phenomena. What are these two principles? First, the principle of relativity that says that the laws of physics are the same in all inertial reference frames. Or in other words, the physics is the same on a train and on the station. Second, the principle of constancy of the speed of light. In other words, the speed of light is the same for all observers independently of who emits that light and independently of the speed of who emits that light. This means that if I am on a train traveling at v and I flash a torch forward, I will observe that light travels at z, but another observer on the station will observe that light also travels at c. Only with these two principles we are going to change our view of the universe. Let us use these two principles to perform some Gedanken experiments, which means thought experiments in German, the language that Einstein was using at that time. First, consider the doctor is traveling on a train and is moving to the right at the speed v. The doctor places a light bulb right at the center of her train wagon, and at the two ends he places two detectors that goes ding.
Is a machine that goes ding
when light hits it. The doctor turns the light bulb on, light is emitted and travels in a spherical wave, then light arrives at both ding detectors simultaneously. Let me draw a space-time diagram for this. I will represent the x-axis as my horizontal component and the time as the vertical component. For practical reasons, instead of plotting time, I will plot CET, which is just time multiplied by the speed of light. This is a convenient way to represent time in relativity. Look that by doing this, time has units of distance. If we measure the distance in meters, we are measuring the time that light needs to travel 1 meter. We will talk a bit more about in detail about this a bit later. Using these units, the trajectory of light will be a straight line making an angle of 45 degrees. It travels 1 meter of distance in 1 meter of time. Because the doctor is on a train wagon, she and both detectors are at rest. They are in the same inertial frame. Therefore, the trajectories of both detectors are 2 vertical lines. This means that they stay in the same x-coordinate as time moves to the future. The trajectory of the doctor is another vertical straight line going up, going to the future. To the trajectories on particles in space-time diagrams, we will call them world lines. Now, let me draw the world lines of the beams of light coming from the light bulb. Because light always travels in 45 degrees in these space-time diagrams, in these relativistic units, I can draw these 2 lines going to the right and going to the left. Because everything is symmetric here, both beams of light arrive at the ding detectors at the same time. They are synchronous events, so this takes place at the time t ding and this takes place also at the time t ding. So all the points in the horizontal line that unites them represent the same temporal moment. This is from the train dragon's reference frame. Now assume that Missy is on the station and sees how the train is moving to the right at the speed v. For her, the train moves to the right and also to the future, so it will be moving tilted right and up. Let me represent the space-time diagram as seen by Missy, which is in a different inertial frame. For this other reference frame, I will use the prime coordinates to distinguish from the train's reference frame. Both detectors on the train move to the right, so their world lines will be these 2 tilted lines. And the detector's world line is parallel to the detector's world lines. They move with the same speed. What about the world lines of the beams of light now? Well, light has the same speed as seen by all observers. This means that light always makes a 45 degrees angle, which happen to arrive at the detectors at different times. This is telling us that the ding events are not synchronized in Missy's reference frame. Let's think this a bit. We assumed that the speed of light is the same for all observers. We applied the same physics in both reference frames. And we ended up with the fact that the 2 events that are synchronized in one reference frame are not synchronized in the other reference frame. Simultaneity is not an absolute concept, but depends on the reference frame. It is not an absolute. This is the first non-intuitive result that we found by just imposing the 2 principles of relativity. The principle of relativity and the principle of the constancy of the speed of light. This might seem very odd, but there has been a huge amount of experiments that verify this result. And it is something that we use every day. We'll continue with this topic in the next lesson, and may the science be with you.